100,000-ton aircraft carrier has just emerged from dry dock after 15 months of critical repairs. The $13 billion USS Gerald R. Ford is over 1,100 feet long and carries the power of a floating air base. But a hidden propulsion error once nearly prevented this monster from returning to sea. In January 2018, the USS Gerald R. Ford was forced to return to port due to a serious propulsion system error. Specifically, the error was identified in the main thrust bearing, a vital component of the propulsion system. The main thrust bearing is the primary support bearing that receives the thrust from the propeller shaft system and transfers that force into the ship's hull structure. According to a report from Claims Journal, the root cause was not the ship's overall design, but was related to machining errors. Mechanical machining flaws from the contractor, General Electric, created dangerous weaknesses in a component where failure is not an option. For a supercarrier longer than 3 football fields, the propulsion system is used for more than just simple movement. It determines the ability to maneuver, maintain position within a carrier strike group, respond to threats, and support the tempo of flight operations on deck. When the main thrust bearing fails, the greatest risk is vibration spreading through the shaft line and putting pressure on the entire drivetrain. If left unchecked, vibration can lead to overheating, abnormal wear, shaft line damage, or force the system to reduce its load to avoid a major failure. In a worst-case scenario, a serious propulsion incident could cause the ship to lose its standard self-maneuvering capability. And an aircraft carrier that cannot maneuver is no longer a symbol of power, but becomes a massive target in need of protection. A second incident dealt another heavy blow to the Ford's operational capability in 2020. During a sea trial, the EMALS system experienced a failure in the power handling system. This is the system that processes and releases electromagnetic energy to launch aircraft, instead of traditional steam catapults. According to USNI News, this error left the Ford unable to launch aircraft for 5 days. If propulsion is likened to the legs that help the Ford move, then EMALS is the arm used to launch planes into the battlefield. An error in the legs reduces maneuverability. An error in the arm causes the carrier to temporarily lose its most important function, launching aircraft. EMALS doesn't just need electricity. It requires a system to process, store, and release energy extremely quickly to create the electromagnetic force, to propel aircraft off the deck in seconds. When the power handling system malfunctions, that energy flow cannot be fed into the launch system properly. The $13 billion ship remained a giant block of steel at that time, but its main punch was locked. These two incidents show the price of putting next-generation technology on a 100,000-ton platform. The more modern the systems, the more they require absolute precision. Sometimes what stops a $13 billion supercarrier isn't enemy fire, but a silent mechanical detail deep inside the ship's belly. These errors forced the Navy to bring the Ford back to dry dock for thorough inspection, dissection, and repair. If you feel proud that a massive system like the Ford is still controlled by technical discipline down to every small detail, comment proud. Because true strength doesn't lie in never breaking down, but in how it is repaired to military standards. Maneuvering an 1,100-foot object into a narrow dry dock is a feat of marine engineering. The USS Gerald R. Ford possesses immense inertia, meaning every movement must be calculated in advance. In the narrow space of a dry dock, primary steering force usually comes from tugboats, harbor pilots, and the port coordination team, as using the ship's own propulsion could increase risk. A team of tugboats surrounds the supercarrier, controlling the bow, stern, and lateral movement. Just one strong gust of wind, a shifting tide, or a push at the wrong angle, and the $13 billion ship could collide with the dock walls. Alignment requires precision, measured in inches, where harbor pilots and technical teams must observe every marking, every line, and every distance between the hull and the dock wall. Once the Ford is positioned correctly in the center, divers and engineers check the support blocks beneath the water. These are blocks arranged according to the hull's load-bearing diagram. The entire 100,000-ton weight will soon transfer to these blocks instead of being supported by the buoyancy of the water. If these blocks are misaligned, the compression force could be transmitted incorrectly into the hull, causing deformation, stress on internal frames, or new damage under the hull. The Ford's load distribution is very complex because the weight is not evenly distributed between the island, flight deck, engine compartments, and internal systems. Once the position is confirmed, massive pumps begin to drain more than 100 million gallons of water from the dry dock. This process happens slowly to ensure the ship settles onto the support blocks in a controlled manner. As the water level gradually drops, the hull, rudders, and especially the propeller shafts begin to emerge into the light. At this point, the ship is no longer supported by hydrostatic pressure, but gradually rests on the support system in the dry dock. Engineers must closely monitor any signs of settling, list, and trim. Any unwanted movement could create stress on the hull, increasing risk for the repair process itself. After months of operation, the hull below the waterline may be covered in moss, sea salt, and marine life. Draining the water completely allows engineers to access underwater fittings that are normally unreachable. This is the moment the true body of a supercarrier appears. The hull, rudders, propeller shafts, shaft lines, load-bearing areas, and systems usually hidden by the ocean. There is no concept of just push it a little more to make it fit here. With the Ford, one wrong push could turn a repair bill into a budget nightmare. Every action is monitored by measuring equipment, inspection procedures, and structural engineering teams. With the Ford settled in the dry dock, the shipyard's machine shops begin the major surgery on the propulsion system. The focus of this repair is handling and recalibrating the main thrust bearing that failed in 2018. This bearing is located deep in the engine room, connected to the shaft line and the propeller shafts. Accessing this part requires dismantling or opening auxiliary systems, shielding layers, lubrication systems, and areas related to the shaft line. A bearing is not just a small ball bearing. It is a massive mechanical assembly that handles extreme loads related to rotational force, axial force, heat, vibration, and the alignment of the entire drivetrain. The first step is to check the damage extent on the bearing surface and housing. Engineers look for signs of heat, wear, or scoring caused by uneven friction. Shaft alignment is also remeasured using specialized equipment to ensure the shaft is not misaligned after the operation and repair phases. If the shaft is misaligned by even a tiny fraction, it can create severe vibration when rotating under heavy load. The alignment tolerance for systems like this is extremely strict, often measured in thousandths of an inch. At this scale, a small misalignment is not visible to the naked eye. But when the shaft rotates for hours, it can turn into heat, vibration, wear, and new failure. After installing or servicing the bearing, the lubrication system must be cleaned and the operating pressure checked. Lubrication is the lifeblood of the propulsion system, ensuring an oil film always separates the heavy load metal surfaces. Engineers must also check the vibration baseline to compare with specifications when the ship is operating at sea. Every measurement must be documented, inspected, and verified. The shaft line must be confirmed straight and stable from the internal drive area to the propellers outside the hull. Once the calibration is complete, protective covers are closed, and the ship prepares for the flooding process. Every silent mechanical detail deep inside the ship's belly has now been restored and checked to rigorous standards. The technical team must ensure no tools, loose components, foreign objects, or errors are left behind in the engine rooms. The Ford is ready to regain its buoyancy and face even more rigorous testing at sea. The process of moving the Ford out of dry dock begins by flooding the dry dock in stages. Massive pumps begin to reverse to bring water from the outside into the dock. However, the water pumping speed is strictly controlled to avoid creating rapid pressure changes around the hull. The rising water must be smooth and stable so as not to create turbulence around the hull, exert unusual impact on the support blocks, or move the ship before it is ready. When the water level reaches calculated marks, the ship begins to lift evenly off the support blocks. This is the most sensitive moment as the ship's weight transitions from resting on blocks to floating freely. Engineers closely monitor list, trim, and balance through measuring systems and direct observation. They must ensure no part of the hull gets snagged on the blocks as the ship rises. If one end of the ship floats significantly before the other, stress on the hull structure can cause deformation or unwanted torque. When the Ford is fully afloat and the water level in the dock is equal to the outside water, the caisson will be removed. The caisson is the massive steel door separating the dry dock from the outside water, which endured great pressure while the dry dock was drained. Opening the caisson marks the moment. The Ford leaves the enclosed repair environment and returns to its actual operating environment. However, even though the propulsion system is repaired, the Ford should not yet operate under its own power in the narrow space of the port. A professional fleet of tugboats will take over navigating the ship out of the dry dock position. Tugboats pull and push the Ford at an extremely slow speed, often near the level of feet per minute, to ensure every movement is under control. The inertia of the aircraft carrier is immense. Once in motion, it cannot stop as quickly as a smaller ship. Tug crews must constantly read the currents, wind, and inertia to adjust thrust. The distance between the hull and the dock wall can be very limited, so every pull and push must be precisely coordinated. Every command from the bridge team must be executed instantaneously by the tugs around the bow and stern. Harbor pilots act as conductors, coordinating between the tug fleet, the shipyard team, and the watch crew on the Ford. Just one small mistake in the push angle could cause the $13 billion ship to scrape against hard concrete structures. Immediately after leaving the dry dock, the USS Gerald R. Ford does not head straight to sea, but stops at the pier for pierside testing. This is the stage to verify that the newly repaired areas, joints, and bearings are watertight, stable, and operating within specifications. Engineers check vibration, temperature, shaft behavior, and lubrication performance of the shaft system. Next is the fast cruise, where the crew operates the ship as if it were offshore, even though the Ford is still at port. Damage control, combat systems, communications, and watch teams are all activated to check synchronization. Then, the Ford goes to open water for sea trials, accelerating, decelerating, turning, stopping, starting, and increasing propulsion system load. This is when the new bearing must prove it can handle a real load. The EMALS system is also verified through dead load testing, launching sleds that simulate aircraft weight. The advanced arresting gear must prove its ability to stop aircraft weighing up to 50,000 pounds. Radar, communications, and crew training are also checked, as a carrier only truly returns when both machinery and people are working in rhythm. When the USS Gerald R. Ford officially passes its tests, the United States has returned a strategic piece to the global chessboard. The Ford is not just a ship, it is a floating airbase, a power plant, a command center, and a weapons platform that can deploy power to vital seas without depending entirely on land bases. The Ford class is designed to achieve a superior sortie generation rate, capable of performing up to 270 flights per day during peak situations. This creates continuous fire pressure on any opponent. The Ford's return also helps relieve the load on older Nimitz-class ships that are gradually reaching their service limits. Strategically, a carrier strike group led by the Ford can create deterrence in hotspots like the Western Pacific, Persian Gulf, and Mediterranean. It reassures allies, forces opponents to recalculate, and allows the U.S. to maintain air power without being fully dependent on land bases. But behind those $13 billion blocks of steel is the silent human element. Behind it are shipyard workers, engineers, Navy inspectors, harbor pilots, tug crews, and sailors. Those who measure every thousandth of an inch, pull every single foot, check every step, and retrain the entire process to bring the Ford back to a state of readiness. The Ford's true power lies in the ability to control the entire system, with precision down to the smallest detail. When every link works correctly, that block of steel doesn't just float again, it returns as a tool of American power at sea. If you like videos that explain directly how military systems actually operate, hit like and subscribe to the channel. In your opinion, what was the scariest part? The bearing error, the EMALS error, or the moment of pulling the ship out of the dry dock foot by foot? Comment below so we can discuss.